Traditional computers operate in a binary fashion. It's either a 1 or a 0. With qubits, quantum bits, we look at very subatomic particles that operate in superposition, which means they can be in multiple states at the same time. When you measure that state, it can be any number between 0 and 1. It can operate a lot faster when it comes to solving things that are optimization and things that are simulation.
What is a quantum computer? So a GPU is something that helps you accelerate particular tasks, like AI. A quantum computer helps you accelerate certain other tasks. The tasks that we think they're going to be really good at include optimization problems. So that's really useful in banking or in the oil and gas sector, where they have some really complex optimization problems they're trying to narrow down. Encryption is one of the things that they're probably going to be good at. And the other area that they're really useful for is just modeling quantum systems, which is any molecular level system. So pharmaceutical drug discovery is one of the really exciting areas.
Quantum computer without classical compute is really just a physics experiment. So the place to start is, what physics experiment am I going to run that gives me the quantum system that I can use for computational purposes? The quantum computing process itself is probabilistic. So you get some of the answer from running it once, you get more of the answer from running it twice. So normally actually you run the same circuit on your quantum computer multiple times, maybe 100, maybe 500 times. So in reality, normally you're talking on the order of milliseconds for the actual time running on the QPU. The quantum computer needs a classical compute part. So that's really where this setup starts. So here we just have a standard classical computer. It's a Dell server. What we do there is we do all the pre-compilation work, going from an algorithm to a gate description to machine language that can be executed on the control hardware, and then the interpretation side of the signals that come back. So from the OPX 1000, it produces microwaves and DC signals. They'll be coming out of these ports on the front, and there are some cables missing that will route up through the server rack and come to the top of this unit at the back behind me. This is a Maybell fridge. This is one of the key enabling technologies for quantum computers. So what we're seeing here is actually two cooling units on top of each other. At the very top, we have a pulse tube, which will go from room temperature, 300 Kelvin, down to 50 Kelvin, down to 10 Kelvin, down to 4 Kelvin. So that's 4 degrees above absolute zero. This is actually the brains of the quantum computer. This is the Rigetti Novera. The frequency that this chip operates at is the equivalent of a very low temperature and what will be emitted at that. So we actually have to bring down the temperature of the environment of the chip so that it doesn't get any background noise going in. And obviously noise going in means that you lose your signal and then your computation will not be able to complete. So what we're seeing here is two patch panels. This is where the signals come into what we call the tower. So as you can see, these lines continue on downwards, following the cold finger. So this core that you see of gold-plated copper is to actually just thermalize everything. And at the bottom here is what we refer to as a puck. In here is a PCB and the quantum chip itself. What you're looking at here are these are hand flexible coaxial cables. And these are what carry the RF, the microwave and the DC signals down to the QPU. It does harken back to the early days of classical computing, where you had big switches and vacuum tubes and all that kind of stuff. And that's really where we're at with quantum computers right now. We really want to be able to enable people who are working on solving real world problems with their quantum computer.